All right, 6.3 looks at finding the area under a curve. So the idea here is we have a function, say maybe f of x is equal to x squared. And the goal is, can we actually approximate the area under that curve on, say, some interval? Let's start with the interval 0, 1. So let's see, I went ahead and graphed y equals x squared. It's a parabola, right? So I mean, I could extend this over here, if I wanted to. But the interval I'm interested in anyway is the interval 0 to 1. So in that region. Okay, so I'm not interested in that side anyway. So the goal then is, can I find the area under the curve here in between 0 and 1? So that area. All right. So, I mean, an idea is, let's kind of break up that interval. So I have to pick a number of intervals. So I kind of just pick something. Let's say we pick 4 sub-intervals. So that means we're going to break up that interval 0, 1 into 4 sub-intervals. So we're going to cut it into fourths. Okay, so if I do that, let's see, my intervals would be 0, a fourth to a half, three-fourths to 1. Okay. So what I'm going to do is, I'm going to draw 4 rectangles corresponding with these 4 sub-intervals. Let's look back at the picture here. Okay, so here are my sub-intervals. I've got here, 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 and here. So my goal is fill in these 4 corresponding rectangles. But the question is, how high do I make these? Because I mean, I can think of a few different ways I could think about this. So like, look at this rectangle on the right. One idea would be, okay, if I start on the right side of that rectangle and I end the rectangle there, then, I mean, this is what that rectangle would look like. That would be if I was to use the right endpoint of the rectangle. So that's one idea. Okay, so then I'd have, I guess, an overestimation of the area in that region. So what's another idea? Another idea would be I could use the left endpoint. So in other words, I would come up here, I would stop there, and then that would be my rectangle. That would be if I used the left endpoint of the rectangle. So either way, I'd have an estimation of the area. That one would obviously be an underestimation because I'd be missing the area here. Versus this guy was in this case, this was an overestimate. This would be an underestimate. Okay, and then what's even another idea? So, I guess we'll go ahead and just remove that. So that was looking at using the right endpoint or the left endpoint of the interval. The other idea I was thinking of was, what if I actually took the midpoint of each interval. So I guess I'd have to find the point. I mean, let's see. So I guess the first midpoint would be halfway in between 0 and a quarter would be an eighth, right? Okay, then the next one would be, let's see. So I'd have a quarter, or I'd have 1/8, 2/8 is a quarter, 3/8. Then I'd have 4/8 is a half, 5/8, 6/8 is 3/4, 7/8. So if I take the midpoint of that interval and I use that to draw my rectangle, then that means this is going to be the height of that rectangle. So the rectangle would look like this. Okay. So let's see, what did I have written down up here? So I was looking at, okay, so I think what we'll do is we'll try doing this one by using that midpoint. So let's see, would that be, well, it'll still be, well, that looks like a little more accurate because let's see, as far as the area under the curve in this region, I mean, here, we're really looking for that area. So here, I mean, I'd have an overestimate here, but an underestimate here. So that looks like it would be a more accurate estimate of the area for this function than using the right or left endpoints. Okay, so let's see, find the midpoint of each interval. So but that's what we were doing already down here. So we kind of said, well, I'm looking at these subintervals. Okay, so I'm going to find the midpoint. And so those midpoints, well, let's see, half of a quarter was an eighth, right? The point halfway in between a quarter and a half was 3/8, right? Look back at the picture here. Here's the first midpoint, the second midpoint, the third midpoint, and the fourth midpoint. Oh, but I'm missing a subinterval here. What in the world? So 0 to a quarter to a half, and a half to 3/4, and then 3/4 to 1. Should be 4 subintervals there, right? Okay, so let's see. An eighth is the midpoint of that interval. 3/8 is the midpoint of that interval. Now looking at this one, again, let's see, that's 4/8, that's 6/8. So the midpoint of that would be 5/8, right? This one, 6/8 and 8/8, the midpoint would be 7/8. So those are my midpoints. My x values, at least, for my midpoints. Okay, but those we had already found on the graph here. So then I have to go, well, what would the matching y values be? Because you see how down here, this point that I found here, that's going to be the height of that rectangle, right? So in order to find the area of this rectangle, I mean, I'm going to have to multiply its length, which is a quarter, right, by its width, by its height, okay? So I have to multiply the x times the y here. So I have a quarter, but then I'd have to know, well, what is the y here? What is that height? So that height is f of 7/8, right? Should I go ahead and draw the rest of the rectangles in while I'm at it? So here's this next midpoint, 5/8. So point's right about here. So that's going to be what I use for the height. Of that rectangle. So again, that rectangle, let's see, its base is 1/4 again. Its height, here, its y value, I'm going to have to actually plug in the 5/8, right? To get the value, y value at that point. There's the next rectangle. Okay. So once again, the base, it's 1/4. To get the y, I have to actually evaluate the function at that midpoint value, 3/8. Okay, and then one more rectangle. This one's a little small. And like so. And so that's f of 1/8. So I have to figure out what each of those y values are. Okay, that's how I'm going to be able to find the area of those rectangles. Just cleaning this up a little bit. And we can go back and add to this, but let's go ahead and evaluate the function. So the function is x squared. Okay, so an 1/8 squared is 1/64. 3/8 squared is 9/64. 5/8 squared is 25/64. And 7/8, oops, 7/8 squared is 49/64. Okay, so now I get to attempt to estimate the area. So let's see, so what the heck are we saying? So let's see, f of 7/8. That's this guy. That's that 49/64. Okay, so what we're saying is, look, this base is 1/4, right? This height is that, I'm going to use this one, is that f of 7/8, which is 49/64, right? So that means to find the area of this rectangle, I would multiply the base times the height, right? So the area of that guy would be 1/4 times 49/64. Okay, I mean, in general even, I'm looking at, I mean, what is the 1/4? That's the, you could say the base of the rectangle. Okay, and then times f of x sub n, say. Okay, so like that's thinking of this as like x sub 1, x sub 2, x sub 3, x sub 4, okay? But anyway, we're just saying the area of that rectangle is the base times the height, okay? look at another one. So let's see. The next rectangle, this one. Again, the base is still a quarter, right? All of these guys have a base of a quarter. And the height, however, is f of 5/8. So we found that above. What was f of 5/8? 25 over 64. Okay, that's the height here. Okay, so again, to get the area, I multiply the base times the height. Okay. So next one, the sky. Okay, so same thing. The base is a quarter. The area is going to be the base times the height. So it was f of 3/8, it was 9/64. Okay, so need some more room. Base times the height. And then the last one, this rectangle. Okay, so the area of that one is the base and then times the height, f of 1/8. Okay, so then, what we're doing here is we're going to fill in, we want to sum up the areas. This area plus this area plus this area plus this little area. That way we have an estimate for the area under that parabola. So that means I've got to add up these 4 terms, the areas of each individual rectangle. So let's see, I have a quarter times a 64th. I have a quarter times 9/64. Quarter times 25/64. And a quarter times 49/64. Okay, so just have to simplify this. I don't know. Could factor out the quarter. Then I already have an LCD. So let me see, 10, 35, is that 84? 64th? Let's see. What does that reduce to? Well, I can divide, let's see, 84 divided by 4. That's 42 divided by 2 is 21. Looks like I get 21/64. So approximately 0.328. Okay, so this is my estimate of the area under x squared. So maybe I should write a little statement. Clean this up. So this is the estimate of the area under x squared between 0 and 1. So in other words, what did I actually find? So one more time. What I actually found is the area of these 1, 2, 3, 4 rectangles. Now that would give me an estimate of what I'm really interested in, which is the area under that quadratic function. Okay? Looks like a decent estimate. Okay, so should I say anything else about this? Let me just point out a couple things. This expression that I have over on the right here, this guy has a special name. So what I actually have here is, okay, so if I have, say, n subintervals, I have like, well, let me say it this way. This guy here, this 1/4, that's the length of each rectangle, right? So here's another way I could write that. I could say delta x. That's like the change in x, right, for each interval. So look at the intervals again. Each rectangle, the change in x is 1/4, right? 1/4, 1/4, 1/4, 1/4. Say delta x, in this case, was 1/4. That means the change in x. And so generally speaking, I could say delta x. And then how did I get, well, the 1/64th? That was like f of the first x value, right? In other words, that was f of 1/8. That gave me the y coordinate here. Okay, and then I'd have delta x again. What was this one? That was f of the second x value. Okay, so then delta x again. This was f of the third x value, and then one more, f of the fourth x value. Okay, and then what else was I going to tell you? This thing is called a Reimann sum. Okay, so what did we do there? We used 4 subintervals. We found the Reimann sum, and we used that Reimann sum to estimate the area under y equals x squared. So you can kind of see, well, the more rectangles that I use, the more accurate the estimate I would get for the area under the curve. In other words, I mean, if my rectangles were even smaller, and we'll do, some more examples, but if I did tiny rectangles, something like that even. Okay, the smaller the rectangles that I choose, the more accurate estimate I would get, because I would be, leaving out or overestimating and underestimating less. Okay, so the more rectangles I use, the more accurate the estimate I get for the area under the curve. So because I only used 4 rectangles in this case, my estimate's probably, just okay. Okay, but the more rectangles you use, the more tedious this process becomes of finding the Reimann sum. So here's another example. Okay, for the function, f of x is 3 minus x. Use a Reimann sum to estimate the area under f of x on the interval 0 to 2. Use 5 subintervals. Okay, and then I started with use the left endpoints of each rectangle. Okay, so let's look at what the goal is. So my goal is find the area under this curve between 0 and 2. This actually happens to be a line, okay? So I'm just trying to estimate the area then. Okay, that chunk. So I've actually graphed the line already, as you can see here, because 3 minus x, that's a negative x plus 3. So isn't this a line in slope-intercept form? So the y-intercept is 3, the slope is 1. So to graph this, I start at 0, 3, down 1, right 1, down 1, right 1, down 1, right 1. Okay, so that's how I graph that line. So now let's look at the calculus part. Okay, so it says use 5 subintervals and the left endpoints of each rectangle. Okay, so my interval is 0, 2. Okay, so I have to break that into fifths. So the length of that interval is 2, right? So that means if I break that up, each subinterval length is going to be 2/5, right? Because I have to divide that entire length by 5 to get 5 subintervals. Okay, so let's start by just writing out what the subintervals would be then. Okay, so 0 to 2/5. Okay, then 2/5 to 4/5. They have to have length 2/5, right? 4/5 to 6/5. 6/5 to 8/5. And 8/5 to 10/5 would be 2. Okay, so you can see there I have 1, 2, 3, 4, 5 subintervals, which is what we were asked for. Okay, so then let's see. This one says use the left endpoints. All right, so that means that starting with my first interval, that starts with 0. So the left endpoint would be here. Okay, so let's see, I did this in fifths, so here's 2/5. So using the left endpoint, trying to draw that so it looks decent, something like that. Okay, there's my first rectangle. Okay, next one, 2/5 to 4/5. So the left endpoint's going to be here. Looks something like that. Okay, left endpoint. There's 8/5. And finally my last interval. Okay. So then to find the area, I have to actually write out my Reimann sum. Okay, so you can see each of these rectangles, the length is 2/5, right? So for each of these, the delta x is 2/5. That's the length of each of these bases. So to find the area of, say, this rectangle, I multiply the base, 2/5, times the height. So the height of that guy's 3, right? Or in other words, I mean that guy's 2/5 and then f of 0. Okay, but look back up here at the function. F of 0 is 3, right? So I don't know, I can write it out in this notation first if that's helpful. 2/5. And then the next one is, look at this rectangle. So the height of that rectangle is f of 2/5, right? The next one, this rectangle, base is 2/5, the height is f of 4/5. Okay, the height of that guy is f of 6/5. And the last one. Height of that one is f of 8/5. Should I finish this up here then? Maybe I'll finish it below. Let's see if I can move this part down. Get some more space. Let's see if that's enough space. Okay, so finishing this off. Okay, so again, the function 3 minus x. Let's finish filling in this Reimann sum. So 2/5, f of 0 is 3. Okay, f of 2/5. Let's see, 3 is 15/5. So what is that? 13/5. Eleven fifths. 9/5. What is that, 7/5? So this is my Reimann sum I'm using to, oops, estimate the area. Then I just have to do the arithmetic. What is that? 15, 28, 39, 48, 55/5? Fifty-five-fifths is 11. So 22/5. So I get approximately 4.4. Okay, so what have I actually found? So I've actually found the area of all four, or all five rather, of these rectangles. Okay, so you can see that would actually be an overestimate of the area actually under that curve, right? Because that's this area, yeah? Just that area. So I've got an estimate. So what I actually found here, it's an estimate, it's actually a overestimate of the area under the curve on the specified interval. Okay, so now we're going to look at the same function, but we're going to look instead at using the right endpoints of each rectangle. So what does that mean? That means I'm still using those 5 subintervals. Same as before. Okay, so then let me draw my boxes again. Need to move this guy just a little bit. Okay, so there's my 2/5, 4/5, 6/5, 8/5, and 2. Okay, but this time using the right endpoint. So I'm starting at the right side of the rectangle. and that's going to be the height that I use. So the height of the rectangle now is going to be f of 2/5. The height of that rectangle f of 4/5, f of 6/5, f of 8/5, and finally f of 2. So you can see this time, when I sum up the areas of these rectangles, I'm actually going to get an underestimate of the area of the curve itself. Because I'm not going to be accounting for these chunks. Okay, so let's set up the Reimann sum. So each rectangle still has a length 2/5. Got 2/5, and then let's see, f of 2/5. So that was what, 3 minus 2/5, so that was 13/5. And then f of 4/5, that's 11/5. F of 6/5, 9/5. F of 8/5, 7/5. Then the last one, f of 2. Well, that's 3 minus 2 is 1. Okay, so those are the areas of each of those rectangles. Then I just have to do the arithmetic. Let's see, 24, 33, 40 divided by 5. 40 divided by 5 is 8, plus 1 is 9. Get that right? So 18/5. Approximately 3.6. So what I have here is then an under estimate of the area under the curve in between 0 and 2. Okay, underestimate. So I guess, what could I conclude? So up here I found an overestimate of the area to be 4.4. Here I found an underestimate of the area to be 3.6. So I guess I could say something like the actual area must be, in between 3.6 and 4.4. So that's kind of cool. So the next section here, 6.4, is we're going to look at, well, how can I actually find the precise area under the curve rather than having to estimate the area? So that's what's coming next.